In this video, we'll talk about an efficient algorithm for identifying which examples to abstain on to optimize AuPRC, starting from the calibrated probabilities. Before we dive in, we'll go over some background on AuPRC, specifically the connection between AuPRC and average precision. To illustrate the connection, we'll go over an example. Imagine we have a vector of binary labels of length n that are sorted in ascending order by their predicted probabilities. How do we find AuPRC? First, remember that the precision is defined as the number of positives above a threshold divided by the total number of examples above that threshold. Our first step will therefore be to find the number of positives ranked above each index. Let this be AI, and it can be found by taking a running sum of the labels yi from right to left. We also need to know the total number of examples above each index, which is simply n minus I. Using those two values, the precision ρi at each index can be found by dividing the number of positives above the index by the total number of examples above the index. Finally, the recall is the number of positives ranked above an index divided by the total number of positives. We use n plus to denote the total number of positives. To get the value of n plus, we can simply look up the value of a0, which in this case is 3. We can now generate a precision recall curve by plotting the precision at unique values of the recall. Note that the recall changes at the indices of the positives. Thus, we can create our curve by plotting pairs of precision and recall values at the positive examples. If we now approximate the area under the curve using a right rectangular sum, note that the rectangles are all evenly spaced with width equal to 1 over the number of positives. Since the height of each rectangle is ρi, this means that the area of each rectangle is ρi divided by n plus. Because we are only plotting the rectangles where yi is 1, the total area of all rectangles, which we will denote as q, is the sum of yi ρi divided by the total number of positives, which is nothing more than the average precision over all those positives. That is why in scikit-learn, a commonly used function for computing the AuPRC is simply called average precision score. We will use this definition of AuPRC in our optimization algorithm. We're now ready to start explaining our algorithm. First, let's build some intuition for what happens when examples in a particular window are abstained on. Let's revisit the example from before, and imagine we abstain on the examples at indices 3 to 5. Let's establish some useful notation. Let n denote the total number of examples, and d denote the number of examples abstained on, in this case 3. Let I0 denote the start of the abstention interval, in this case also 3. That means I0 to I0 plus d denotes the range of indices abstained on. We will use WI0 plus to denote the number of positives in the abstained interval. In this case, WI0 plus is 1. We can now go through and compute the new values for the number of positives above each index after abstention and the total number of examples above each index after abstention. Also, we can compute the precision at each index after abstention. Notice that for all indices that lie above the abstention interval, nothing changes. For indices that lie below the abstention interval, the value of AI decreases by WI0 plus, and the total number of examples above decreases by d. The precision at these indices after abstention is thus AI minus WI0 plus divided by n minus I minus d. Let delta I0 ρi denote the change in the precision at I after abstention. After simplification, we have that delta I0 ρi when I is less than I0 is equal to d ρi minus WI0 plus divided by n minus I minus d. Now that we've seen how the precision at individual indices changes, let's look at how the total precision changes. Let's revisit our example from the previous slide and add the values of yi ρi to the slide, both before abstention and after abstention. This is simply the precision masked according to whether the example is a positive. Let's use t to denote the total precision at the positives. Before abstention, this is 2.17. Let's denote the change in t after abstention as delta I0 t. As we saw in the previous slide, for indices above the abstention window, there is no change in the precision at positives. For indices that lie below the abstention window, the precision at the positives changes by delta I0 ρi. And for indices that lie within the abstention window, we simply lose the precision at those positives from the total. Putting it all together, the change in the total precision at the positives after abstention is given by summing up yi delta I naught rho I at examples below the abstention window and subtracting away yi rho I at examples within the abstention window. How can we efficiently compute the change in the total precision for all possible values of I naught? If we substitute in the formula for delta I naught rho I that we calculated earlier, we get the formula shown. We can then split this into three separate terms and define bi naught, ci naught, and di naught as shown. After some inspection, it turns out that all of the terms needed to find delta I naught t can be computed in O of n time for all values of I naught. Specifically, bi naught is a sliding window sum of yi rho I, ci naught can be found via a left to right running sum, di naught can also be found via a left to right running sum, and wi naught plus is a sliding window sum of the positives. If we know the change in the total precision, and we know the number of positives in the abstained window, we can easily find the change in the average precision. In other words, we can find the change in AuPRC for all abstention intervals in O of n time. Putting this all together, we can finally write out our algorithm for AuPRC optimization. The inputs to the algorithm are 1. The vector p of calibrated predicted probabilities sorted in ascending order, 2. The number of examples d to abstain on, and 3. The number of Monte Carlo iterations m. The output will be a vector delta, where delta I denotes the estimated change in AuPRC if examples from I to I plus d are abstained on. The algorithm proceeds as follows. First, delta I is initialized to 0 for all relevant I. Then, in each Monte Carlo iteration, binary labels yi are sampled according to the probabilities pi. The quantity ai, denoting the number of positives above index I, is computed for all I via a right-to-left running sum, and n plus, denoting the total number of positives, is set to a0. The quantity rho I, denoting the precision above index I, is found for all I, and from these, the average precision score q is computed. The quantities wi plus and bi are found for all relevant I via a sliding window sum, and the quantities ci and di are found for all relevant I via left to right running sums. From these, the value for delta I is incremented to reflect the change in AuPRC that would be produced by abstention in this Monte Carlo iteration. Finally, the values in the vector delta are normalized by the number of Monte Carlo iterations m and returned. Every step in the Monte Carlo loop takes no more than O of n time, so the overall runtime of the algorithm is O of mn. If you wish to skip the Monte Carlo sampling, you could omit the sampling loop and substitute the probabilities pi for yi, which would result in an O of n algorithm.